Okay, now that we've completed preparing the trace files, and we have two trace files now, one's called myreport.txt and one's called myreport2.text, it's time to start having a look at it. So starting in 22, we're going to start doing an analysis of what we produced in the previous steps. So the first thing we want you to do is work with myreport.txt. It was the first one, and it's the larger one of the two of them. Okay, and we suggest, because we didn't turn on recursive SQL display, there are lots of extra things in here. It's good to go and look at it with an editor, something like gedit or VI. It just makes it easier. We can find individual statements. So since that's their idea of using gedit, let's go and do that. Okay, they should be in the trace directory now. They should have got dumped in there. We've got my trace file if you want to have a look at a raw trace file, and it is mildly interesting looking at a raw trace file. So we'll do a little more in that and just see what it looks like. Making this full screen just makes a lot of sense. It doesn't wrap as much also. And we'll just take a quick look at this. This is a little extra to the practice, but I think it's quite useful to get an idea what's in there. And then you appreciate the formatting that tkprof does for you. So what it does is it identifies itself as a trace file. We merged a group of them together. So it just says this was done by a certain process. Okay. And then it starts with the trace file, and we have weight information about a cursor. Then we have information about parsing a cursor. And then this is the cursor they were parsing. And this probably wasn't part of our application code. This is probably a recursive call that's being processed by the SQL. And this is another one that I wouldn't see this typed in the application. This is another statement. It parsed this cursor, and then it went through and says, this is the time it took to parse it. And that's just a timestamp from the beginning of a certain time in the past. And then it took some time to execute it. And then it took some time to fetch it. Okay. And it also dumps out information in the trace file about the execution plan that I was actually using. The stats are about the execution plan. But because of the way they format it, it's kind of difficult to read. They close it, they execute it, they fetch, they do a bunch of things with this cursor. And there is a whole bunch of them. Eventually we'll find one of the select statements that they put in. And some of them have a massive amount of executes. And it becomes very difficult to read, so when they format it, it makes it much easier. So let's quit looking at this. We'll just quit out of it. And let's edit this, our actual output reports where we formatted them. Let's edit them with gedit. Now this is a big file. It takes it a moment or two to load up, so you have to be a little patient with it. And then it takes a moment or two as you search through it also, because it is quite a large file. Myreport.trace. It's loading it up. It's a big file. Once again, it makes it easier if I make it larger. Now, what it says is this is produced by tkprof. This is on 12C release 1 base version. 12.101 was the base version. The patch set 1 is out there already. It makes it 12.102. We haven't installed it on this class. This class predates the availability of patch set 2 being out there. Then it says I was produced from this trace file called mytrace.trc. The sort options are the default. We didn't put in a sort to sort the data, so we're just dumping it out the way it was in the trace file. And then it gives you the summary of this little table when you're executing individual. What the count means, what the CPU, the elapsed, we already discussed that, but it just gives you a reminder. Shows you an SQL ID and a hash plan value. This is the execution plan, the official title for it in memory, a hash value to look it up. And this is a select statement, and it's not one I would have typed as part of the application. It's one of the recursive calls, and this is some information about its performance and the execution plan that it was doing. It just goes on and on through the recursive. Now it makes it a little easier because we're used to this format because we've had a look at it a few times as we look at it. But as we're analyzing the file, we want you to focus on certain important things instead of reading through the whole thing. It doesn't a good novel make. Okay, it's easier to search for the things. So the first query we're going to look at has this string in it, okay, without the quotes on it. So what we can do is search for the ordered space use underscore hash S2. It's one of the queries and we want to talk about it in it. So their intent is for you to go to this file and you can just do Control F to pull up the search, paste in what you want to search. I get rid of the quotes because it's a string. They wanted you to enter the whole thing, but it doesn't actually have quotes on it on the hint. Okay, and find it. And that will allow us to find the area that we're interested in. And what I do is just make it the top so it's a little easier to read. So a little more than I wanted. And notice there's a lot more of the trace file. We're just looking at part of the trace file. And this is doing a select. These are the resources it takes. And this is the execution plan that it used. Okay, and these are the information about the execution, about the different steps. The first run of it averaged over all the runs and the max number of rows we saw, the maximum. We just want to know, usually the average interesting, but are there wide variations or are there close? Since this was only run one, it was one for each of them. The max and the value and the average were all the same, and that they're all exactly the same on these. So now, as part of this guided practice, we want you to observe some behavior. Okay, so find the first example in the trace and then find the second occurrence. So just do the find for the same string and look at the two of them and see what you think of what it took to execute them. Now in the practice we show you theirs, and it sometimes wraps a little bit when you have a look at the execution plan that makes them a little hard to read. But there are two copies in here and we want to have a look at the two of them. So let's do that first and then read through their description of what was going on in their little script file. Okay, so this was the first execution. It had to touch a fair number of blocks to return one adder. It was a count again. That's one of their favorite queries. From joining two copies of the sales table with itself as an equal join. Okay, it's a self join. Okay, it may not return anything too sensible, but it was interested. It did it as a hash join of the two tables. If the two tables are the same size, because they're just copies of the same thing, it doesn't really matter which one it uses. Generally, when it does a hash join, it will try to use the one on the top will be the smaller table, but these are the same. It couldn't differentiate between them. Okay. We also dumped out the wait messages. We noticed we did a lot of reads and writes to the temp file. Okay, so that meant it had to do some sorting or it overflowed some information. Okay, as part of this. Okay, so we did some reading and writing to temp is usually, unless we're doing a direct read, okay, it usually means we're actually doing a sort somewhere along the way. And then we did some other reads and waits, but they were the biggest, the reading and writing to temp. We also did some direct reads, not to temp. That means we did some direct reads of data off a disk directly into the PGA of my process while we were executing this. Now there should be another one in there, so do the Control F, not G, Control F, Trevor, and find it again. Okay, and this should be the second one we executed. It should be a little down just to make sure. Okay, this was the second one. Let's see if it's different. We looked at the same number of rows, but we found a little less. Find it again. We should find it back at the top. It did more disk reads in this case. Find the second one again. And it's even more disk reads. Okay, so we can compare the two of them. This time it did the join on the two of them, so this looks like the data we were looking at before. Find it again. This is the other copy. It did the same thing essentially, okay, with a little bit different statistics. The time is a little different because now we have a little more efficient read and writes when we sort. We have to do less I/O. So what is going on? This one looks a little more efficient because the timings are different. If we compare that to the previous one, okay, its timing were a little longer, 43 and 86. And the difference is we did much more writes, we did less. Now, why the heck did that happen? Well, let's go see what they say in the book. Okay, in case one illustrates the consequences of using manually sized SQL area parameters such as hashed area size, sort area size, etc. Since we were doing a hash join, when we build the hash table, we'll talk about the hash processing in the future, but when we build the hash table, it builds it into memory and then it overflows to the temporary table space. And we use it as an overflow. We can only have so much memory. If the hash area size is very large, we have to do less spillovers and the chunks are in bigger pieces, so we do less writes, okay, for the same amount of data. If the area is very small, we do a lot smaller piece in memory. We have to write more pieces out, and then sometimes we have to reread them to resort and rewrite them out again. So how well the hash join, and we forced a hash join intentionally, performs to a great extent is how much area we have to build a hash table in memory. This was using the old style, not using the PGA aggregate to tune it, but the old style of setting individual parameters. And in one case, we set it very small. That caused more time to be used to process a statement. We executed the same statement with a larger hash area size, and it took less time. They have their same data up here. The numbers may slightly vary from yours or from what I observed because of the behavior, but generally you should find the second one a little faster, and the reason why the logical reads and writes to the temp are a lot less. So let's move on to the next step, which is 23. Interpreting the case number 2, okay? In this trace, the first statement of interest has the string use literals, okay? And this is a very long trace. What do you conclude about it? So we want you to just have a look at it first and see what is going on for the first example. So go back to this and look for that string. I guess it would be a little easier if I just grab it from the file and I don't have to type it in as much. Makes my life a little easier. We're just working with the same trace file. We're just searching for a different string within it. Use literals, find that. And this is the one we tagged. This was a PLSQL anonymous block, okay? And in this block, we're going in and calling the DBMS package. I like to confirm to make sure I am looking at the right thing, so I just go have a look, and sure enough, that's what they show here. So let's go have a quick gleam of what's going on. We have an outer loop that loops 5,000 times. We're parsing the statement, okay, that we're executing, okay, and then we're defining the columns, and then we're executing it. Okay, then we decide if we get any data, and if we get some data back, we write a message out to indicate it. And then we loop back. So every time we execute this statement, we force a reparse on it. Okay, and by using the DMLS thing, it's just a select from one of the internal tables, object name, from the DBA underscore objects, just to give us an interesting question. Okay, what we find in this case is the parse is relatively cheap. We did that once, but the execute is expensive. Okay, because we execute at 5,000 and we really reparse it each time and re-execute it. So it makes the execute expensive. And we should have a second version in there. So in the case, an almost identical statement was run 5,000 times, each time a different literal was used in the query. This caused the system to parse the statement to build a new execution plan and to store a different execution plan in the shared pool, which is relatively expensive and it's inefficient. Although the time precision is too low for accurate information, the parse time for each, okay, and the execution time is relatively high. Confirm that these 500 executions are executed at recursive level 1. And then when you actually have a look at the data, it will actually say a little way later that it was executed at recursive level 1. Okay. Now we're going to go and see if there's a difference. So a little while later, the SQL we're executing within it, we execute each of them once, and we do a whole bunch of them. Okay, and we're executing them at recursive level 1. Okay, so we can continue scrolling down and have a look at it. Okay. And then we find this next execution, which is another execution. It goes on and on. That's why they said it was a really long file. They didn't look at all of them. Another statement was also executed 500 times in SESB, but this version uses the bind variables. So we're looking for the statement that has the tag on it, use bind variables, to compare it to our previous one. We'll put that in the paste buffer. I just did a Control-C to do that. Go back to our report. Okay, I'll just close this for now. We should scroll down. We'll find that it's executed a number of times. And we have a whole group of execution plans. I'm not going to look through 5,000 of them. I get a little tired of doing that. They're parsed once, executed once. Each of them is treated through this loop as a separate SQL statement. I just wanted to show you there were a lot in there. So let's go find the second version with the Control-F. Replace the string with use bind variables. Go find that. It's a little later on. Took us a minute. You know, there was a little pause to go find it. Now we're basically doing the same thing, but now instead of passing in a different literal, that was driven off the loop. Okay, what we're going to do is parse it once with a bind variable and rebind many times and see if that improves the execution. To parse the PLSQL block, we just parsed it once and executed it once. We parsed the statement within it once, and that's it. Then we move on to a different statement, which is really some recursive calls that it would have been a little nicer if we removed them by using the sys equals no, but they didn't, so we use the search to find them. And that was just demonstrating now it takes less resources overall. Each of those executions didn't take long to parse and long to execute of that simple SQL statement, but we did it repetitively. It added up to a lot of time. Doing it parse once and executing it many times with different literals is a lot more efficient way of actually doing it. So we wanted to illustrate, so that's just how you write your code. We were just using a certain way to show it, but if we use Bind variables where it's appropriate. We'll get more efficient code in our application than if we use literals for everything, especially if it's fundamentally an OLTP type application. So we showed you the information. I looked at my example. They show theirs. That theirs wraps a little worse than mine did because I made it nice and big. This is looking at case 3, okay? And we're looking for the string update sales amount is 2,000. Now, I may just look for the end of it and type in the sales amount. When we get a wrap on the end of the line, it was a really bad place to put a break. It should have been shoved onto the next line and made as one string. It would have been easier to search for. So I'll just type the update in myself just to make sure we don't have problems with it. Put it in the paste buffer, go to my file, look for a new version of it, okay? And then go to the front and put update in front of it, just so we can find what they wanted us to look for. And it wasn't too far further down. It has the update, the set amount sold to 2,000. That was the start of it, okay? This executes. The parse was cheap. The executes, because it was an update, had to visit lots of disks to update 2 rows that caused a total of 4 blocks to be updated. Now, the 2 rows may have been in 1 or 2 blocks. That's the 2 scenarios. But the other 2 blocks, if they were on 2 blocks, were the undo segments header we had to update and the undo data that we had to write into that undo segment. Represented at least 2 blocks we had to update. So when you actually update 1 block to update data, we actually end up updating 3 blocks on disk because we always generate the undo information first, because we never know if you're going to roll back the transaction or commit it generally. And to do this update of 2 rows, we had to punch 4,441 blocks in query mode to find it to cause our update of 3 blocks to occur. Is there a better execution plan? I'm thinking it's a full table scan, and sure enough, we used a full table scan on it. If we could give it an appropriate index, maybe it would be a better access path for it. So let's go back and review. So if you look closely, you see the access. This is the complete table to update only 2 rows. This is very inefficient. An alternate case is much better because it speeds up with an index. So this is their first execution, doing a full table scan. We also have the wait events. We did wait for I/O, but it was less than 1/100th of a second, so it's not a significant wait for the I/O. And we waited for the client, but they were pretty fast. We were driving it with a script file. Script files don't have much wait time in them, okay? Then we go in and have a look at another version of it, which has an index. They didn't tell us to search for it, so I suspect it's right below it in our file. All we have to do is scroll down a little further. It has the one we did. Now we're changing trace files. It does do that as a statement, interesting enough. And then we find our second update statement. Update the sales. I guess I could have searched for it, but I just scrolled down. It looked like it was pretty close. The first thing we notice is the execution time is quicker. We have to go up to find the previous one, up a couple. So it took 0.06, got it in about the same. My machine was pretty idle. Now, when we actually do the update, it's less than we can measure. When we actually update the 2 rows, we're touching only 3 blocks in query mode, and we're updating 3 blocks. I still suspect that the 2 rows are on 2 different blocks, okay? The difference is the segment header for the undo is probably in memory. So it only have to update the 2 blocks, and one was cheaper to do it. It had to only touch 1 block at this time to add the information it did. And this gives us, using the index, gives us a better access path, so it scales much better as the data gets larger and that. And that's what they wanted to see in this case, okay? So the next task is interpret case 4, which was generated by step 13 above. This trace can be found below the string called myTrace4, so we're just going to look for this and have a look at what they're doing in there, and then we'll come back and read their comments. So they just want us to observe, and then we'll talk about it a little bit. So replace this, find it, and it occurs just below it. So we're turning on tracing. This is the information for that statement. Go a little further down, and we should find our statement. This looks like something, a recursive call they were doing as parsing. Okay, and then we'll go find our statement, or hope. What does their statement look like? So we found the alter session. And they were just talking, it does one fetch, so we alter the trace. Okay, and then we find the update for the select star from sales with the amount greater than 30,000. So let's find that statement. I may have scrolled over it. Let's back up a bit. So here's the start of our trace file 4. This is turning on the trace file. Okay, this was another query. It doesn't look like the select we were looking for, so more recursive calls, as I mentioned. Scroll over that. This is more recursive calls. Scroll over that. More recursive calls. Like I mentioned, we should have got rid of these. Okay. At some point, I get tired of looking at it, and I'll probably just search for it. Okay. Some more recursive calls. More recursive calls. As I mentioned, if we removed them, it would have made life a lot easier. So let's search for the select statement. I'm getting tired of looking for it. Maybe I just missed their search criteria for it. In this case, they don't talk about it, but it's the alter session. And we're looking for select star where sales history amount is greater than 0. We should just find the next statement, and I'll just scroll back up just to make sure I didn't miss it. There's always the risk that Trevor just missed it. So we'll back up and find the start of the trace file. It was about here. Make sure we're here, and then we'll search down for the end of their select statement. I get tired of looking for it. So there we go. We put it in a dynamic SQL, wrapped it as dynamic SQL, and executed it. Okay. Now this one, when we parsed it, not too bad. When we executed it, wow. It took 14 seconds to execute it. Okay. Now, why did it take so long? The waits time was short, and we were just updating one row. So let's go have a look at the execution plan. Because it was dynamic SQL, it didn't show it to us, so let's see what they have. So this was expensive to execute. So let's take a look at their statement. Okay, my trace file. There is the statement. And they show it with the fetch. So what we saw is the wrapping they did of wrapping it. We still didn't find the statement. So let's go find it again. Okay, here we go. Here's the one we want. Now we see it's already being dynamically parsed. We're just looking at the execute time was trivial. The fetch time, we fetched it many times, okay, to return a few number of rows. We just happened to do it many times. And we did a full table scan to solve this of the 28 partitions with a partition range scan of all of them. So we're just doing a full table scan on each of them. And it took us a fair amount of time to do it. So let's go have a look at it. Okay, so we just go in and look at it, observe it. Okay, in this case, the first statement does use the fetch mechanism appropriately. One fetch operation is done for every single row retrieved. this is very efficient. The alternate case is using 95 fetches to retrieve the same amount, where they used, in their case, a very large number of fetches, one for each row that they went in. So this increased the number of fetches substantially. We can do it, and we can do it if we're doing it in SQL+. They probably set the array size in SQL+ to 1. We set the array size larger, and what we found with testing it, setting it up to 1,000 improved performance. Above 1,000 seems to be diminishing return, but going 100 instead of 1 is more efficient. Doing 500 is more efficient, but by the time you get to 1,000 for most queries, it's diminishing returns. You won't actually get any advantage. So what we want to do is reduce it. So we're going to look for the next version of that we happen to do as dynamic SQL. So here's our process in this one, but we changed the way it was processed. Okay, go find the SQL we were processing when we execute it. Now we did it at 92. Now the execute time is down substantially. It's down to just over a second, where with the original case it was just over 4 seconds. We cut it into quarter of the time. And the number of blocks we needed to look at, we should have also reduced. Okay, so we went from 19,138,8843 that we had to look at to this. By doing it, chunking it larger, we made the whole process a lot more efficient. So some other things that we hadn't considered within the lecture material. So they were just showing us the difference between the two of them. Next is step 26. We need to interpret the trace files for case 5, which was generated earlier on in step 14. This trace file can find by using the string union all. Okay, what do you observe and what are your conclusions? Well, let's have a look at it, then the review what they are intending us to find after we have a quick look at it. So back to my report file, we'll look for the union all. Whoops, I didn't get it pasted in. I suspect that because I didn't cut it, so let's go do that again. Fingers are getting tired. No doubt. We'll go have a look at this. Replace it. Search for it in our file. Okay, and this is our select servant. Insert into sales to select from as a union, and with the select from that. And we do a union all. Okay, we observe it took about 2 seconds to do this. Took us a little longer to get the time. It may be some wait time, so having the wait events is useful in these. So we spent some time, and the biggest chunk of the time we spent waiting is waiting for local writes to occur. So that's interesting, and it was 2.5. We also spent a little time for log buffer space and log buffer switch when we were processing. So we're inserting data. Some of it is the redo information processed into the redo logs. They gave us a little wait time. The biggest is the local write wait that we actually have on doing the writes for it. Okay, so what else can we observe? We had to touch as part of this insert as a select, as a DML statement, a large number of blocks in current mode. We're inserting new data. We have to get it from the original tables, so we're querying them. Okay, the 2 of them, so we're querying them. Okay, and we inserted a large number of rows. So this is a massive update that we're doing that took some time to do. Okay, so we're going in, and to do the union all, we're doing a full table scan of the 2 tables. Okay, one is a partition version of the other one, union them all together. The other one we're doing a range scan, but all of them. Okay, one we made a copy of it that was non-partitioned, the other one is partitioned, union together. and then we're inserting them as a conventional load. That does regular inserts to the database buffer cache. It has to generate undo in case we want to roll it back, okay, or the statement fails, and we have to generate redo in case we have a power fail or another issue to redo the operation if it got completed. So that generates a lot of additional information. Is there a more efficient way of doing it? Perhaps. Perhaps as we did it without the conventional load and bypass the SGA processing. So in this first statement, notice a large value associated with the execute phase. Here the first statement incurs too many recursive calls to allocate extents to the table. This is because the table space which is stored is not correctly set up for the extent allocation. We allocate them in small chunks. The symptom may be a number of statements that follow this statement have messages recursive depth 1. This recursive are not seen if sys equals no, and the recursive calls are due to do the space management for a dictionary managed table space. Okay, the alternative case, which starts with the next statement, contains the string union all, is much better as we see. The time for the execution is much lower, so let's go have a look at it, and then we'll see how they did it, talk about a little more about they did it, and the reason why we set the table space up better. Okay, so we'll find the union all again, so we have basically the same statement. Now we set the table space up a little better, we hope. Okay, the execution time with 1.9, that's an improvement. The elapsed time was a little longer. Once again, we're doing a conventional load. We're doing the full table scans, and we're inserting a large number of rows. Okay. And in this case, we have the local writes we're not waiting for. We got ahead of it. In exchange, well, we still have the local writes in there. Okay, so we try to set it up a little better. Okay, so how do theirs look? Okay, so theirs showed a little faster, if that's the same statement, when we updated it. But that was other recursive calls in there. So we tried to set it up a little better. It didn't actually work from what I've seen in it. Okay, I would still like to see this statement done with an append hint. I think it would run much faster, and that might be an additional improvement to it. But we're moving on and having a look at case number 6, okay, which starts at 16. And the trace file, the area we're interested in, starts with this interesting string. They had to find a way in their case, which is actually their ID, SQL ID. Let's see if they use the same SQL ID in ours. Sure enough, they did. Okay. And this is a select customer ID, sum of number from sales group, ordered by, so it looks like one of our summaries just against one table. And it has a group by function in it, except it was wrote kind of interestingly. Okay. And this was relatively expensive to query. We had to touch, okay, about 1/3 of a million blocks, just under 400,000 blocks in query mode to return 7059. So that makes me suspect there may be a better execution plan available for this. We did a full table scan on the sales table, then did the sort for the group by, so we forced a big sort on it. And things were going on. When it wanted to buffer, it had to wait, but it was less than hundredths of a second. That's not too long. The big time was waiting for the log switches for a checkpoint to complete. Okay, because change information. This is a query. It wasn't making the changes. That was a side effect from our earlier insert. It was still suffering from the poor performance from that to a little bit, I believe. Okay, and if we look at the execution plan, it did a full table scan. Maybe an index would help out. But let's see what their conclusions are. This case is more difficult to understand. Here you have selected a table that is entirely locked by another transaction. This forces the query to generate read-consistent blocks for almost the entire table. So it has to make a copy of the blocks and roll them back, causing, if it has to, causing unused segments to be accessed. This is shown by a large query value and almost no current blocks when they look at it. So we get large query, but almost no current when we're looking at the rows. And the second thing is maybe we had a better access path that would also help in that case. But they were just looking at the fact that they had locked the table with another transaction and then run the query. We don't need locks to do the query, but it has a side effect in how we process the blocks for the query that can have a negative impact on performance. It costs us a fair time to execute this. Okay, if we didn't have to, if the table wasn't locked, it would have been a lot cheaper to execute it. Next up is step 28, where we're having a look at case 7, okay? And what we want to do is take a look at case 7 and see what we collect. And what we're going to do is compare the contents as my report.txt, which is really just one statement at the end, with what we did in my report.toText. You can see that something was changed because it came up with a different execution plan. It can be fooling. And the query we're looking at, okay, is the one that does this select, okay, from our customers too, and does a group by operation in it. Okay, in the first one, we have to look at a lot of blocks. Costs us a relative amount of time to return one row because it's a sum operation across the grouping, and there's only one set. It does a full table access. There may or may not be a way of reducing it, but we didn't really use, we're looking for a particular customer ID and then doing the group by the customer ID, so it only returns one grouping. Maybe if we had an index it could use on customer ID, it might be useful. For some reason it chose to do a full table scan. And then said did a sort group by, but it didn't really sort because there's only one sort, and used the result cache. We stored the information in the result cache. Okay. This is, if we take a look at my report 2, you notice the row source, okay, has a full table access, okay, and the explain plan shows table access by index. This indicates the explain plan is not accurate in the second one. Somebody added it, but we have the explain plan from a different time. That's just an indication that there's a misconnect. So we see they have did a full table access, but later on we have an index with a index mode. So that indicates when we created the execution plan, between the time we collected the trace file, where the trace file said we did a full table scan, and we built the execution plan that said it used an index, somewhere in between that time somebody added an index. So watch the explain plan output from these. It can be fooling. Finally, there's a little step to clean it up in preparation for future practices. I'll just start this off and it just does a little cleanup. And then we're done this practice. That's the end of the practice. So Let me start that off just to prove that we actually completed the practice. I'll have to exit out of my report. Okay, we should take a quick look at report 2 just to say we did it. Okay, I thought I exited out of it, but apparently I didn't. Okay, get rid of, and then go up and have a quick look at report 2. In this one, we actually, we should have got rid of the recursive calls also. This is the one where we're doing our group by function in a parse call. And when it actually did it, reading this from the trace file, this is what it got from the trace file. And for the previous ones, we didn't actually ask it to do the explain plan. But when we got it to do the explain plan, it says right when the tk-prof was run, because there was a new index, I would like to do a table access full on it, okay, using an index somewhere in here. And so they added an index between the time we did the full table scan and the time they did it in their exam. In mine, they hadn't done it, so it's a little different. So they were basing theirs on their file. The last thing we got to do is go run that little file that cleans up, and then we're done with the practice. And it didn't take long, so we've completed practice number 3.